Okay, it is a great pleasure to have with us from far, far away, from a galaxy redshift 4 and beyond away, Dr. Tanio Diaz Santos. As you all know, Tanio is a researcher at the Institute of Astrophysics. He obtained his PhD back in 2009. Then he moved in Madrid from the University Complutense de Madrid. And then he moved to Crete for a bit over 2 years as a postdoc. And then he moved to Caltech for a bit over 3 years, working with Lee Armus. And then in 2014, he went as a CONICET fellow to Santiago, Chile, where he was there for nearly 6 years, working mostly on higher redshifts than he did his original work, and extensively with ALMA data. And then we were very fortunate that Tanio was very interested to come back to the island paradise and apply for a researcher position at the Institute of Astrophysics. He has been with us for the past 3 years, and he is up for tenure and promotion to the next position. So he will share with us what he has been doing over the past few years. Tanio, it's up to you.
Thank you very much, Vasilis. And first of all, I would like to thank everybody for being here. I don't take it for granted that that many people are attending seminars in the afternoon when they could be at the beach. So it's a pleasure to have an audience. So today I would like to talk about the interstellar medium of the most luminous galaxies that we know of, both in the near universe and far away at high redshift. And I would like to talk about the latest results that we are having, both in the nearby universe with JWST, latest results obtained within the last year, and also in the high redshift studies that that we have been carrying out, especially with ALMA, but soon hopefully also with JWST, of high redshift obscure galaxies at cosmic noon and beyond. So the talk is going to be divided in two, in results from the nearby universe and the far universe. But in any case, I would like to motivate why we should care. Why we should care about luminous infrared galaxies in general as a population. And as you all probably well known is that the definition of luminous and ultraluminous infrared galaxies are sources with infrared luminosities in excess of 10 to the 11 solar luminosities, and in the case of ULERGs, up to 10 to the 13 solar luminosities. And if there is something that I would like you to take away from this talk, is here in the first slide, right? It's that ULERGs and LERGs are perfect laboratories to study the triggering of dust-obscure starburst via galaxy mergers, and to understand the convolution of star formation and supermassive black holes accretion across cosmic time, right? Because we know that most galaxies are living their lives in a steady state in the main sequence of star-forming galaxies, right? But we know from simulations as well that at least once over their lifetimes, they will experience an interaction with another galaxy. So studying these interacting galaxies is a vital part of our understanding, if we were to understand how galaxies form and evolve across cosmic time. So luminous infrared galaxies were discovered in the 70s, but it was not until the 80s when IRAS was launched that we could take a systematic look at this population of galaxies. And we realized that basically they were emitting the bulk of the energy output in the far infrared wavelengths, as you see here on the left. I think you can see my pointer, I guess. Right, so these are infrared luminous galaxies, which it is true that they are not numerous in the local universe. They don't represent a high fraction of galaxies in the nearby universe, but they are the dominant population that contribute to the total luminosity infrared luminous density of galaxies at high redshifts, starting from redshift 1 and beyond. And not only LERCs and ULERs dominate the infrared output, but this population as a whole, infrared galaxies, are the ones that dominate the global star formation rate in the universe at cosmic noon, between redshift 1 and 2 to 3. So I'm going to start with the results that we have been obtained for near infrared galaxies in the local universe. We have been putting a lot of effort into understanding the interstellar medium of these galaxies based on the GOES sample. GOES stands for the Great Observatories All-Skyler Survey, which is a complete local galaxy sample containing all the systems with infrared luminosities in excess of 10 to the 11 solar luminosities, included in the 16 micron selected revised bright galaxy sample. This, with the Spitzer, we managed to disentangle these systems into 290 approximately individual galaxies that span infrared luminosities between 10, actually a little bit lower than the LER classification, 10 to the 10 to 12.3 solar luminosities. One of the most important properties of this sample is that it covers the entire merger sequence, as you can see here in all these nice thumbnails. They cover the entire merger sequence from isolated disks to widely separated pairs to latest mergers in which the galactic nuclei have already coalesced. Also, an important point of this sample, and why it's key to study luminous infrared galaxies, is that they span a range from main sequence galaxies to starburst and quasars in the local universe. So it's the perfect sample to understand why galaxies jump out of the main sequence. So what we have been doing during the past year is to study the ISM of these galaxies with JWST, with the early release science program, this number here. Anyway, the focus of this program is to study the physics and star formation, black hole growth, and feedback in these 4 luminous infrared galaxies that you see here. I will tell you a little bit more detail about that later on. But we have observed them with NIRCam and MIRI in imaging, as well as with NIRSPEC and MIRI MRS IFU spectroscopy. And together with ancillary data sets, we have observed these galaxies with Chandra, HST, Spitzer, I mean, all the telescopes that you can imagine, with the goal of measuring the stars, gas, and dust on sub-100 parsec scales. Right, and the total amount of time awarded to this program was almost 40 hours. So the key questions that we are trying to answer are basically these 3: how stars form and black hole growth in merging galaxies, how do they impact these energy sources, the ambient interstellar medium, and what are the implications for models of fueling and feedback. This is a reminder how JWST has improved our vision on not only these galaxies, but in general of observations in the mid-infrared, right? Because it has improved in sensitivity, 50 times in sensitivity, 10 in spatial resolution, and 5 in resolving power over what we had before with the Spitzer IRS. So it will transform studies of the multi-phase ISM of nearby galaxies and anything basically, and all galaxies, as you know, at the high redshift. So the 3 observables, class of observables that we will be focusing on and that we are getting information of are these three. Basically, they are ionized atomic gas lines that tell us about the ionization structure, density, and properties of star-forming clumps, as well as narrow line regions, jets, shocks, winds, etc. We also have access to the warm molecular gas. With MIRI, we have access to the pure rotational transitions of the H2 molecule. And with NIRSpec, we can access the first vibrational state. So we can do temperature diagrams, we can calculate masses of warm molecular gas, we can study the dynamics and feedback as well via shocks and turbulence. The third of the observables are basically dust in the form of PAHs, polycyclic aromatic hydrocarbons, and dust continuum from black body emission. And with these observables, we can basically estimate the sizes of dust grains, the ionization state of those grains in the photodissociation regions. We can infer the ambient radiation field and also have a clue of the energy balance of these all components. The science topics in which I will discuss the results that we have been obtaining are these three. Basically, we will focus on the nuclear star formation and stellar clusters, for which we have been able to measure the star formation rates, sizes, ages of the star forming clumps and nuclear starburst. Also, we will be discussing about the identification of new AGN that were previously not known in some of these galaxies. And we will be able to characterize in general, the nuclear power sources. Finally, we will focus on the feedback that these nuclei have over the gas that is surrounding them. We will map the extent and impact of the feedback and circumnuclear gas and dust at different scales. So these are the ERS targets that we have observed. I will not bore you with the details, but just to tell you a little bit more about this. NGC 7469 is an earlier interacting merger whose main component has a safer 1.5 nucleus, which is surrounded by a circumnuclear ring, a strong star-forming circumnuclear ring, which is located at around 1 arc second from the nucleus. 2Zwicky-96 is a merging pair, very luminous, in which, interestingly, the two galaxies that we see here are not the main contributors to the total infrared power, but it is basically a very tiny source that is in the overlapping region that accounts for most of the infrared output of this merger. BB114 here, it's also an interacting galaxy. One of the galaxies is visible in the optical and has very little obscuration, and the other is highly obscure and it's only started to be visible in the near infrared and beyond. And finally, NGC 3256, it's a later stage merger that also contains two nuclei. One is visible and the other it's not, but for this galaxy we have obtained the data very recently, so we haven't been able to do any preliminary analysis on it. So I will be discussing basically results from these three. So to start with the first science topic is basically cluster formation and destruction. And for this, we basically made the assumption that galaxies form a cluster in a steady state, right? So in this case, we would have the same number of optical clusters or clusters in general per H beam, right? If there is nothing that destroys them. But if there is a mechanism for destruction of these clusters, we don't know what it is yet, But we would be looking at a power law, at a slope that is not constant, but it has a slope, right? And we know from HST observations that mergers can actually drive higher rates of cluster destruction. As you can see here in the middle panel, you see that the slope is consistent with a -1 slope in log dNdt as a function of log year, which means that for every decade of aging, we see a decade of destruction, meaning that 90% of the clusters are destroyed within 1 decade of in age. Not only that, we know that in mergers, even if the slope as a function of infrared luminosity of the sources doesn't change much, we have seen that for more infrared luminous sources, we have these sources are able to form more clusters at a given, more massive clusters at a given cluster mass, right? So we have cluster destruction, and on top of that, cluster formation, but also similar destruction. So, in fact, in a study by Linden et al. And collaborators, we have seen that the cluster destruction in luminous infrared galaxies, in the most luminous galaxies that we know of in the nearby universe, right? The cluster destruction is happens at a higher rate. The slope is larger than in less luminous galaxies, right? But while we have seen these differences, we haven't been able to access the ages where the most young stellar clusters are. And this is because at these earlier stages, all the clusters tend to be very obscured. And with HST, it was impossible to detect them because they were very faint in the optical and in the near infrared. But in a very recent paper of this same group, Linden and collaborators, they perform a study or a detection of clusters in BB114, and they detected 374 compact star clusters candidates with NIRCam in various broadband filters. And we saw that 20% of these sources are actually undetected at optical wavelengths. You can see them all here in this red box over here. You can see that they are very red in the color of 1.5 to 2 micron, and also very red in the color of 2 micron to 3.5 micron. And you can appreciate that the position in the parameter space of these sources here, it's only explainable only if you have, if they are very young, basically. They are very young and very extinct. That's, you can see here, the AV vector. So we have detected basically a hidden population of young clusters that quadruples the number of young, massive, and dusty sources that had been identified in BB114 until the time. A similar result we have obtained for the ring of star formation in NGC 7469. Actually, Bond and the collaborators identified that 80% of the JWST sources have very near infrared colors. Here you see them in red. They show extinctions, very high extinctions, up to AV of 7. And not only that, but they probably, in order to move them into this region of the parameter space, you need a contribution of hot dust that make the filter at 4.4 micron over luminous. So more than half of these sources are coincident with 5.6 micron emission peaks, which means that indeed we are looking at hot dust. And their near infrared colors are also consistent with the youngest sources previously detected in HST. So, and then again with BB114, we see here for 7469 that JWST has increased the total percentage for young stellar clusters from 15 to 48%. Here I have put a little panel showing that now we are able to get into the realm of clusters and detect the very young clusters with ages less than 10 mega years. So in terms of the second science topic, what powers these luminous infrared galaxies, this is the case of 2696. We have here in the upper right image. This is the source that I was telling you before that whose infrared energy output is dominated by a until the date unresolved source detected at MIPS 24 with a Spitzer that look like it's coming from nowhere, right? Here there is nothing. But with JWST, we have been able to not only detect the source, but also resolve it. And actually, in fact, a single compact source here, D1, is responsible for up to 70% of the total infrared energy of the entire system, right? And what is more puzzling is that this source is not even bright in the near infrared. Here is an HST image, D1, and it's not the brightest. There is this complex A here that is much brighter. And also, not only we have identified the source of this mid-infrared emission that we saw with the Spitzer, but also we saw that about half of the star-forming sources detected at 5.6 micron with JWST are obscured and discovered for the first time. And I want to step and dedicate one slide to actually this source, D1, because I would like you to ponder the I don't know how to say the power of this source in itself, right? This we are talking about an unresolved source spanning at most 150 parsec, right? And this accounts for 3 to 5 to 10 to the 11 solar luminosities just by this source, right? Which together with the upper limit on the size puts a luminosity surface density lower limit of 3 to 5 times 10 to the 12 solar luminosities per kiloparsec square, which is comparable only to superstar clusters and Euler nuclei, actually. So consider that this source here overpowers the entirety of all the system that we see in here, right? So in addition to that, we see that structures have a very complex and wide range of colors, which tell us that the extinction is very patchy and extremely complicated in these interacting systems. So highlighting the need for high resolution multi-wavelength observations of all these galaxies. Also for BB114, we have imaged and targeted with IFE observations only the east nucleus, which is the obscure one. The other is only visible in the optical, right? As I mentioned before. And for this source, we have resolved the nucleus into 2 cores. And we have identified in the southwest component that this source is likely powered by an AGN. And this is because in the spectra, in the near infrared spectra of this source, we see that there is almost no polycyclic aromatic hydrocarbon emission, which the pH equivalent width has usually been used as a very reliable tracer of not only of the detection of AGN, but also on the quantification of its power, as it is supposed that the hard ionization field from these AGNs is able to photodestruct pH molecules, therefore reducing their intensity as well as dominating the continuum at 3 micron from hot dust, reducing the total equivalent width. So this is basically the smoking gun of the existence of the AGN. On the contrary, the northeast core is mostly star formation dominated because we have a strong pH emission as well as a strong silicate absorption, which all points out to very obscured and intense star formation. And finally, on the third topic of this nearby universe section, I would like to talk about feedback on the ISM, and I will do it for this galaxy only, 7469, but at different scales. And I will start with what happens and the results that we have obtained at the very central source, at the 1.5 safer nucleus that we can resolve, obviously, but in which we have seen asymmetric blue shifted profiles in high ionization coronal lines. Here you can see in all these lines, I don't know if you can read them, but magnesium 5, silicon 9, neon 5, right? All these powered by can be powered by AGN. And we see that they show a blue component, a wing that can extend up to 1700 kilometers per second at zero intensity, right? And you don't see this broad outflowing component in low ionization species here, like for example, neon 2 or argon 2, neither in molecular lines, right? They are all very narrow, resembling just the rotation that is happening at the center. So actually, if you plot the full width of max of all these high ionization lines as a function of their ionization potential, you can see that there is a clear trend, right? And this is telling us that we are probably looking at a decelerating and stratified AGN-driven outflow. You can imagine it in the sense that you, as the ionization potential, you have more highly ionized gas moving at faster velocities, and this highly ionized gas can only be excited closer to the nucleus, right? So it's gas closer to the nucleus moving at faster velocities and lower velocities as you move out. So that's why the decelerating part is specified here. So also back of the envelope calculations about the mass outflow rate of this ionized gas put a rate between 0.5 and 5 solar masses per year, while the estimated black hole accretion rate is at least 1 order of magnitude lower than that, which is based on some scaling relations based on the oxygen 4 emission line, which means that basically the AGN is evacuating gas at an order of magnitude higher rate than it is accreting it, which means that, I don't know what is not a very ill-fated future for the AGN. So we can look now at a little bit larger scales and look at also the highly ionized gas, in this case, magnesium 5, right? And we can see that in this case, we detect also highly ionized gas on more extended regions, and also extending, especially resolving it towards the east of the galaxy. This is highly ionized gas wind, which is likely hitting the surrounding dense medium at a distance of around 200 parsec is from the AGN. In addition to that, we also detect disturbed molecular gas, H2. This is the velocity dispersion map, very disturbed molecular gas, but interestingly not in the direction of where we detect the high ionization lines, right? So it is unclear up to now whether this shocked gas is being excited because of interaction of the outflow of the AGN with the surrounding medium, or is excited in situ by dynamical heating, for example. So you can have here this is a sketch of the different components, right? The outflowing high ionized seeing winds, east and west and northwest, the shocked material, shocked H2. And we can see and also ask ourselves what is the impact of the feedback from the AGN on even larger scales, right? In the sense, is this feedback affecting the star-forming ring? So in a paper by Lai and collaborators, they extracted mid-infrared spectra in several apertures along the disk, across the disk, and a little bit inside, right? And they fitted all the features using a fitting code called CAFE that with which they were able to estimate the luminosity of all the pH features in the mid-infrared spectra. Just as a side note, by the way, is that the extraction tool that we have used, that they have used, to extract all the regions, as well as the fitting code that fits all the near and mid-infrared spectrum, are tools that have been developed here at the Institute. So if you ever deal with JW HT spectra from the mid-infrared de Mares IFU or near spec IFU, just you have an expert here that can help you. So Lai and collaborators basically use these diagnostics of pH ratios to investigate the physical conditions of the pH molecules across the ring. And they saw that in the inner ring, the regions showed that the distribution of sizes, of pH sizes, were bigger in the innermost part of the ring, right? And this coupled together with the fact that there is a trend of this particular pH, right here, 6.2/7.7, as a function of the ionization intensity, right, which is being improved by this neon, this ratio of neon species, right, neon 3 over neon 2. Basically, this correlation points that the changes in the pH ratio is caused by a change in the hardness of the radiation field, right? Which is suggestive of dust processing and photodissociation. And while this is happening, indeed, and we see changes in the pH ratios, these are only confined to the innermost part of the ring. So it looks like the AGN is not having a dramatic influence over over how star formation is proceeding in the rest of the ring, only in the innermost part. So this is a summary of the nearby universe. Yeah, okay. So JWST is not only detecting galaxies at the highest redshift. This is just to make a point that the nearby universe is also delivering very interesting results. It's also unveiling and resolving previously unknown sources at the core of nearby infrared galaxies, right? We have discovered a new population of very young and massive star clusters unidentified by previous HST observations, right? Very obscure, that they account for around 20 to 25% of the total population. The Lyrt nuclei of 296 and BB114 are resolved in several components. In the first one, we are identifying the power source of extreme luminosity, and we have discovered a buried AGN in the later that which hadn't been identified before. And finally, AGN feedback in 7469 is identified in nucleus and its vicinity up to 200 parsec via ionization lines and coronal lines. And we also detect turbulent molecular gas. And the starburst ring at 500 parsec is only being affected by the AGN only at the inner region, where the dust reprocessing is stressed by the pHs, and it has proven that is not changing by much. So I would like to move on now to the second part of the talk, which is focused on the far universe. And I would like to, in addition, I would like to remotivate again why we should care about the most extreme galaxies at high redshift, not only because they are important by their own, but we also have this thing that we call the lambda CDM that predicts a very specific shape for the distribution of mass, the mass distribution of galaxies in the universe, which should look like this dashed line over here. But what we get from observations is these points over here, right? So there is a dearth, there is a scarcity in galaxies at the low and high mass end of this distribution, right? So galaxies are less massive at these two ends. And this basically requires at least one mechanism that suppress star formation and prevent these galaxies to be as massive as lambda CDM is predicting. And there are two regimes. One in the low mass regimes is basically, it looks like it's turbulence-driven star formation feedback. That is the most likely explanation for the halt of star formation rate in these galaxies. And at high masses, it is the momentum-driven quasar AGN feedback that quench these galaxies, right? And well, these two mechanisms have been introduced in simulations, and simulations look like they are able to recover observations quite well. But obviously, these are simulations, and we need to verify and corroborate this observationally, right? Because it's not because simulations tell us we need to believe blindly, right? So this is important. And how quasars may be contributing to this quenching of star formation in galaxies, we have always in our mind like this very nice picture from Hopkins 2008 and collaborators, right? That in which this is describing the paradigm that we have right now for the formation of quasars, right, in the local universe. And very briefly, we can see that it's basically the interaction between two or more galaxies trigger a loss of angular momentum in local angular momentum. And first at the center of the two galaxies, interacting galaxies, then in the second passage at the center of mass of them, right? This loss of angular momentum makes the gas and dust to accumulate in the nuclei of these galaxies, which ignites strong star formation, starburst, and also accrete matter into the AGN, which become luminous. This is the phase in which we have, what we call ULERC, which is basically an obscure quasar in which energy is being produced both by star formation and the central quasar, but is obscured and cannot be seen in the optical. Blowout phase, we have later consequence of the feedback from these two processes, right, that expel the dust out of the central regions, and then we see the typical optically selected quasar, after which, since the star formation has been come to a halt, the entire host suffers a morphological transformation into a dead elliptical galaxy, right? So this is, in very succinctly, the paradigm that we have now for the formation of quasars in the local universe, right? But what about high redshift? I mean, can we assume that this is the same, at high redshift, when we know that at cosmic noon and beyond, the typical ISM conditions of galaxies are very different. So because we know that at cosmic noon, we have higher star formation rates, right? By an order of magnitude higher than in the local universe. We have higher gas content, right? By a factor of 5 at least, than larger than in the local universe. We have higher molecular gas fractions, right? From 20% in the local universe up to 80% up to redshift 2 and above, right? We have higher star formation rate efficiencies or shorter depletion timescales, right? Here, decreasing by a factor of 2 up to redshift around 2. And not only that, but we have also higher accretion rates, right? Assuming that star formation in galaxies have some continuity, we can track them in the main sequence parameter space, and then we can require this continuity in order to calculate how much accretion, gas accretion, these galaxies need to have in order to keep forming stars and moving them progressively in the star formation rate sequence parameter space, right? So, and you can see that from very low redshifts, the accretion rates that you need are very low, in factors of few to up to redshift 2, where we need hundreds of solar masses per year to be accreted, right? So the conditions at high redshift are very different from low redshift. So we cannot assume directly that the formation of quasars or how they are triggered are just via the classical mechanism, which is the collision or the merger of two gas-rich spiral galaxies, right? So in order to shed more light on this topic, we have been studying in the past years a population of galaxies which we have dubbed hot dust obscure galaxies, or hot dogs, which are a population of galaxies that have been detected with the WISE satellite. They were selected to be very strong emitters in the mid-infrared, the W3 and W4 filters, and very weak or basically non-detected in W1 and W2 in the near infrared. This selects for around 2,000 of such objects in the entire sky. And you can see here on the right-hand panel the distribution of sources as a function of redshift, where they peak around redshift 2, but they span all over and into the latest stages of cosmic dawn, right? A cosmic moon between 1 and 3, and with some extreme cases that we will be discussing later, like the galaxy W2046 at redshift 4.6. So thanks to Herschel, we obtained photometry for around 200 hot dogs, and we discovered that most of them, virtually all of them, have infrared luminosities in excess of 10 to the 13 solar luminosities. Not only that, a significant fraction, like 10% of them, had also infrared luminosities in excess of 10 to the 14 solar luminosities, as luminous as some bright clusters. This qualified them as extremely luminous, or EL hot dogs, and most of them are located by selection, not by selection, but because we are detecting them at the, because of the distance, luminosity distance, right? We are detecting them at higher redshifts. So what is the typical SED of hot dogs? This is shown here in this panel as this running average blue dotted line, right? And we can see that this can be reproduced by a power law of temperatures, which have typical cutoffs at the cooler end of around 60 K. and at the hotter end of around 45 to 500 K, right? And the SED of hot dogs looks very similar to that of, for example, type 1 QSOs or type 2 QSO, except in the optical. The SED of hot dogs are really, really obscure. And it's only if you take a template of a type 2 QSO plus an AV, an extra AV of 6, that you can get, not almost, almost not, to the very red colors that characterize hot dogs. And also because of this, because of the red colors and the very high luminosities, we cannot detect, we cannot identify the host galaxy down to wavelengths where we would be able to calculate or see the stellar mass, right, around 1 micron, which are still dominated by the host, by the hot dog. We only can detect the host galaxy in the optical. So this is a remarkably, this SED is remarkably similar to quasars, at least in the near infrared and infrared in general. So that's why we think that these are powered by AGN. So we carry out the pilot surveys with ground-based telescopes to study the black hole masses of these beasts. And based on H-alpha spectra, we have seen that the black hole masses are on the order of 10 to the 9, right? And given their luminosity, the Eddington ratios that we are talking about here are around 1 or above, right? Like these are the most efficient radiators per black hole mass compared with other quasars at redshift 2 in this case, here in the left panel, right? And the particular case, the special case of 20 to 46, which has an Eddington ratio of 3, right? And stands above all the rest of the quasars, optical and otherwise, also dust obscure galaxies. And also has a black hole mass of 4 times 10 to the 9 solar masses. Also, because of this powerful AGN that are buried in dust, these are likely powering massive outflows that we detect actually, again, in H-alpha nitrogen 2 line profiles, as well as, I don't show it here, but oxygen 3 as well. So in order to push forward with the characterization of the interstellar medium of these extreme objects, we carried out a multi-cycle ALMA campaign aimed at studying the ionized gas in a few of these objects, only 7 extremely luminous hot dogs, including 20 to 46. The redshifts are like on the high end on the distribution from 3 to 4.6. And we obtain observations of C+ at 158 micron and the underlying continuum at resolutions that at the distance of the galaxy correspond to a physical size of 1 to 2.5 kiloparsecs. And what we will see is that C+ is an excellent tracer of the dynamics of the system, as well as in terms of the characterization of the physical state of the properties of the ASM on the host galaxy, right? So one of the most important results that we obtained for this pilot sample was that, in fact, hot dogs present a variety of velocity fields, which is a little bit surprising, or quite surprising, depending on your expectations, because we would have expected that most of these galaxies would show similar kinematic property, right? But instead, we have galaxies that almost show no rotation, to very complicated systems that look like that they are rotating, but in reality, no. When you look into the cubes, you see multiple kinematic components. Some other objects that are clearly rotating have a very well-defined rotation curve, and some others that are rotating, but well, they have nearby companions around, so they can disturb the velocity field, right? So these just show that these galaxies have very complex kinematics that may indicate the possible presence of multiple components. What actually a property that actually is common to all of them is that they all show high velocity dispersion, right? All hot dogs show full width of max of the C+ emission in excess of 500 kilometers per second, which points to a very disturbed and turbulent ISM. This is, in most cases, probably likely the consequence of the AGN feedback, but in cases like this, like W0831, it may be also merger driven and caused by turbulent heating or dynamical friction, because we know that there are this probably very compact multiple component system. So the velocity dispersion of the gas may be dominated by the motions of the galaxies. In terms of how the velocity dispersion compare with other populations, we see here that normal star-forming galaxies peak around 200 kilometers per second. Optical quasars selected at slightly higher redshift peak at 350. Slightly lower redshift infrared quasars at 400, but nothing compares to the velocity dispersion that we find in hot dogs, right? In terms of the black hole masses of these sources, we see that basically the black hole masses with respect to the dynamical mass of the host, right? We have here two sources for which we were able to actually perform a proper kinematic modeling. So we know precisely the dynamical mass, and we get the black hole mass from the studies before. And we see that they are, the black holes are overly massive for their dynamical mass, given the local relation here represented by this solid line, but they are not in a very different area of the parameter space when compared with other quasars at a different redshift 6, 3, 4.5, 3.52, right? Like they are all overly massive, but they are not excessively massive. And in terms of the star formation rate properties of the host, here is a plot of the star formation rate as a function of the stellar mass, so the main sequence of star-forming galaxies at each redshift, which are here represented by these thick lines, right? What we see for hot dogs is that we cannot say anything, really. Most of them, they seem to lay on top of the respective main sequence. Some of them look like they are slightly above that, but the uncertainties are very large. Some others are below, right? But these are very low number statistics, so it's difficult to say anything particularly about any individual source. The only thing that we can say is that they don't look to be, as a population, over the main sequence or below, systematically below the main sequence, but they seem to be around it, let's say. And we will need a larger sample of hot dogs in order to really know where they lay. Finally, talking about a little bit about the environment, we know that we have a statistical evidence that hot dogs live in large overdensities. This is from the studies from John, Nassef, and Fan, that through stacking of fields of hot dogs in the near infrared and some millimeter, they established that they were in overdensities, not too large overdensities, like a factor of 2 over the field, but they were likely in dense fields. So thanks to ALMA and to the IFU aspect of the observation, right, where you have information about the space and frequency, we can actually search for companions in hot dogs on a individual source-by-source case, right? And for example, for 2246, which is the most luminous hot dog and the farthest that we know, we detected 3 galaxy companions, one located at 1 arcsecond northwest of the hot dog here, with very low velocity with respect to the systemic of the hot dog. Right, we detected another companion here at around 35 kiloparsec, 5 arcseconds, more or less, and a final companion here that in the beginning we missed, but we understood that we missed it because it was in the border of a spectral window of ALMA, but later we confirmed its existence based on optical spectroscopy, where we detected a very strong Lyman alpha emitter in this region, right? So this is not the first time. This was not the first time that companion galaxies have been identified surrounding high redshift quasars. For example, in a study by the Carly and Tal collaborators, they found that in a sample of more than 20 quasars at redshifts larger than 6, they detected identified companion galaxies in 4 sources and at distances which were slightly high, but still compatible with some dynamical connection between the quasar and the companions, right? At distances below 600 parsecs and with velocity offsets lower than 600 kilometers per second. Also in studies by Tatterbrock and Nguyen, they study, I think it was a dozen of optically and far infrared selected quasars at redshift 5, and they saw that 4 sources showed companion galaxies around, right? So basically, we wanted to go deeper and be able to detect better these companion galaxies in 2256. So we went with, at the time, it was a long expenditure of time with ALMA, 2 hours on source, and we wanted to target the nitrogen 205 line as well as the dust continuum. And what we saw was that we not only detected the galaxies in dust continuum, but we also detected large filamentary structures that were connecting the companion galaxies with the central hot dogs, right, with 2246. And these streamers extend up to 35 kiloparsec, right? And they are also show bridges of dust and gas, seemingly connecting all the components and even overlapping over them, right? And to us, this meant evidence that basically support that the most luminous obscure quasars at cosminute and probably beyond may be fed by tidal streamers accreted from infalling or interacting galaxies, right? If you calculate the infall accretion rate based on all this gas that is surrounding the hot dog, you come up with an accretion rate which is in the few hundreds, right? So you can, with this accretion rate, you can really feed the central host for several hundred mega years at the current star formation rate. So just to finish, coming back to the original question, right, which is like whether the local paradigm that we have on the formation of quasars is applicable at high redshift. So can we say that hot dogs are formed by a single continuous event like the established paradigm for triggering the Euler phenomenon at low Z? Well, we can look at the evidence and see that we are seeing a variety of morphologies. We see both in C+ in dust continuum, right? And we see high velocity dispersion, but we see also distinct dynamical states, very varied, right? Rotating these complex kinematics, slow rotation, etc. Not only that, we see that we see the existence of companion galaxies. In some cases, a few of them, right? I showed only the case for 2046, but we know that there are companion galaxies for all the other hot dogs in the pilot sample. At least 80% of them have companion galaxies. And we see extended structure. This is not something that you would expect in a later stage merger. You don't see companion galaxies. You see the two gas-rich galaxies already coalesced, right? So it seems that extremely luminous hot dogs don't seem to be systematically at the latest stage of a major merger interaction, right? And this to us is supporting evidence, although indirect is true, that a scenario in which extremely luminous hot dog phases could be actually not unique, happens one, but can be recurrent or episodic, even if chaotic, right? Because all these chunks of gas, they will fall chaotically into the host. So, but one of the implications of this scenario is that basically, if you take a look at the black hole masses that these galaxies, these hot dogs have currently now, as I mentioned before, they are on the order of 10 to the 9 solar masses, right? And we know that the most massive black holes that we know today in the local universe are around 10 to the 10, right? So this means that they only, even at redshift 4 or 3, these massive black holes can only grow on 1 or at most 2 Eddington or salpeter times, like an E4 time, right? Assuming Eddington ratios of 1, right? So it means that if recurrent, the extremely luminous hot dog episodes might be really short, right? Because they can only last altogether not more than 50 mega years, or 100 at most, right? So this basically tell us that the extremely luminous hot dog phenomenon may be a very short episodic phase of these massive galaxies. And okay, with this concludes the second part of the seminar, right? I can summarize really quick. Hot dogs are a population of quasar host galaxies powered by accretion into supermassive black holes, right? They are at high redshift and they have volumetric luminosities in excess of 10 to the 13 solar luminosities and are characterized by SEDs containing hot dust. They show a variety of kinematic properties, but all of them high velocity dispersions, suggesting very turbulent ISM. The black hole masses are above the local correlation, but not too different from other high Z quasar populations. And the host seems to be that they are not very far away from the main sequence of star-forming galaxies. And how hot dogs fit into the paradigm of galaxy evolution? Well, it looks like with these ALMA observations that we have been obtaining, they suggest that the dynamical state of the systems is not unique. They are also surrounded by many companion galaxies, which suggests that a possible scenario in which extremely luminous hot dogs may not be triggered by, they are triggered by interactions, but not in the same sense that we think of about the formation of quasars in the local universe, right? And these episodes may be recurrent and chaotic. And as a highlight, just to finish, actually 2246 is scheduled to be observed with JWST next week. So we will obtain near-spec IFU mosaic of the entire merger system, targeting H alpha, nitrogen 2, H beta, oxygen 3, and we will characterize the state and metallicity of the ionized gas and the kinematics from a optical rest frame point of view. We will also obtain MIRI MRS IFU observations of the host galaxy, which we will be able to characterize the dust properties of this source. So exciting times next week. A lot of pressure. Okay, thank you very much.
Thank you very much, Tanio. Are there any questions? Adoni, you may want to.
Hi, Tanio. Great presentation, great results as well
Thank you.
From the local universe all the way to high edge. So my question is on the second part of your presentation. So you presented, I mean, you motivated the thing, the second part by asking the question, what is triggering AGN activity, right? So my comment and question as well, I would be interested to find out what you think is, I mean, those hot dogs, although very interesting, they do represent a very extremely rare population. And I'm just wondering, you know, how can you extrapolate from them to the bulk of the AGN population, which are not hot dogs, right? They are far from.
Yes.
So, yeah.
Yes. So you have a very good point. I mean, we can. The short answer is that with this sample that we have been studying, we cannot, right? Because these are among a very brief phase of in the life of AGNs, which is the obscure phase. We are looking at the peak of the iceberg, right? So obviously it may not be representative of the whole population, not even from AGNs that have been selected at other wavelengths, right? They may be in a completely different stage of their evolution. So what we have been trying is to actually try to expand the sample to look in depth at optical quasars as well, but not only that, to increase the sample of hot dogs to lower infrared luminosities, right? To go deeper into the population where most of the sources are, like not about 10 to the 14, but 10 to the 13 solar luminosity, right? And to be able to go into, to be able to say something more about the bulk of the population. That being said, though, I always like to advocate for, I see the point, and I completely agree with the studying the bulk of the population is always the most interesting, maybe the most interesting point of view, right? But that hasn't stopped us, for example, from studying ARC-220 in the local universe, which is a template for nothing, right? But but is one of the most studied galaxies ever, right? Because there are many interesting physics that may not be happening in the bulk of the population, but models need to reproduce those as well. And right now, they are not.
Yeah.
They can't. So that's also very interesting per se, right? Even if they are not representative.
If I may follow on that, I'm not quite sure I agree with you. I agree with you that, you know, rare objects are extremely interesting, and, you know, that doesn't, you know, something that deviates from the average is definitely interesting. But I would have thought that, you know, like for those particular class of objects, there are models. Like the Hopkins model was made to explain those. The question is whether the Hopkins model is generic enough, right?
Actually, the Hopkins model is only tested in the local universe, right? That is the point, because and I know of, because I'm collaborating now with or try to set up a collaboration with modelers, actually from a collaborator, Daniela Angles Alcázar, with specialized in high redshift simulations using fire, right? To characterize the most massive encounters at high redshift, right? And it's not possible yet, right? Because the machinery is not there. They are not, first of all, they are not able to simulate large enough volumes to have beasts like this. And most luminous sources that they are able to find in these simulations, they cannot treat them properly because the radiative transfer simulations are extremely demanding computationally. So you cannot track simultaneously the MHD plus radiation together. Although now he's putting a lot of effort, they are putting a lot of effort in trying to merge these two aspects and trying to actually, not only that, but generate actual cubes like we see with ALMA, with MUSE, with JWST, to have mock observation as if you look them through telescopes. So you can actually make a apples to apples comparison. So we are getting there, I think.
Great, great, very interesting. Looking forward to seeing all those results. Good stuff.
Thank you. Another question? I don't see Manoli.
Yes, thank you very much, Tanio. Very nice presentation and very, very interesting results. It was very nice to see in your first part of your talk, the detections of the clusters in galaxies. So I would like to ask you if you can say a bit more on the method used for the detection. I guess this is based on the color plots.
Yes.
So the near infrared bands. But is there something more?
So far, well, these early papers focused on color diagrams and comparing these colors with basically SSPs, single stellar population, right? Nothing sophisticated in terms of histories of star formation rates. So that is for once, right? So the point is that all these sources that have been newly discovered, that in a region of the parameter space that where there was nothing before based on NHST. That is the early results, right? Like in terms of statistics, how many of these clusters there are. But there will be more in-depth analysis, right? Like because putting together JWST together with HST, right? And or the upper limits that HST can provide, you can do full SED fitting, photometric SED fitting to the clusters and derive proper AVs, ages, star formation rates, etc. for this. But these are like the rush for publishing. It's in the beginning, you need to, the highlights and the results to get them out, and then go for the more thorough analysis, which are on the works.
Okay, thanks.
I don't know if that answers your question, but
yes, yeah. And maybe just another one on the photos. Probably I have asked you again in the past, but I forgot the answer. So how do you? I mean, in this plot where you calculate somewhere you calculated the star formation rates. You saw a plot that
yes,
some of them are above with these large error bars. So is this calculated through SED modeling or just?
So actually, this that's a very interesting question, because one of the ways that we had to calculate the star formation rate of for the hosts, one of the methods was SED modeling, but actually the referee asked us to remove that. Because the way the models were set up actually introduced a correlation between because it's a normal correlation if you assume just one single star formation rate history between star formation rate and stellar mass, right? They are correlated. So they are not independent. So they tend to actually, it was a very good point from the referee, that would create an artificial correlation, basically. So we decided to remove that and stick with the other star formation rate tracers, like C+, for example, which is not a very reliable star formation rate tracer anyway, but we took two ranges, basically a wide range of possible calibrations. We didn't give just one and etc. like many people do. Just we took two ranges. We also used the dust continuum after removing the component, the unresolved component from that. We did a modeling, a 2D modeling of the spatial distribution, and we assumed that the dust that from the extended regions scale with a certain spectra or templates or black bodies, and then from that calculate a star formation rate. And in fact, the figure that I showed there, like the errors, we decided to go and be as blunt as possible with the with the uncertainties there, and the uncertainties in that plot are not actually statistical uncertainties, but they represent the entire range of values that scaling relations can give you, which is obviously gigantic, right? Like they vary by an order of magnitude. So,
okay.
that's the.
But if you were to use SCD modeling, you have the same trend, or is something different?
They tend to be, if I remember well, they turn to be slightly, the star formation rate tend to be slightly on the lower end, if I remember well. But I would have to check.
Okay, thank you.
And so I'll ask one question since I actually thought about it. You mentioned something about the masses of hot dogs, right?
Mm-hmm.
And how
Stellar.
well the stellar masses? How do you measure the stellar masses? The dynamical, sorry, the dynamical. You said that the dynamical masses are high, but
okay.
do you use gas measurements to get that, or stellar measurements?
So stellar masses came from the SED fitting, which that we can calculate.
Assuming that the AGN decomposition has been done properly.
Yes, yes. So we cannot directly measure the masses based on 1.6 micron continuum, but we can decompose the optical plus near infrared emission into host plus AGN, and then from the extrapolation from the host into the near infrared and calibration of stellar masses based on these wavelengths, we can estimate the stellar mass of the host. The dynamical masses came actually from the ALMA data, but we could only use the 3D Barolo to fit a thin disk, even if probably it's no thing. Maybe there is a disk, but I don't believe there is thing. But this is the only thing that we can use. At least they are rotating, and they are resolved enough to fit an analytic model there and calculate a proper dynamical mass.
Okay.
But it's true that actually it's a very good point, because in the paper, the stellar masses are very, very close to the dynamical mass, which it's a little bit in tension because these sources should be, maybe not dominated by gas, but the stellar masses shouldn't account as much for the the total mass of the system. So maybe there is, I mean, we will figure this out all with the GWST, right? Because WISE has a very poor spatial resolution. So we will be able to, with GWST, look at an order of magnitude higher resolution and hopefully isolate the host better.
Okay, and a speculative question. You know, all these hot dogs, if I remember well, you had mentioned this in the past, where they were discovered based on the All-Sky survey with WISE, right? Effectively, and you alluded that there is sort of like, or maybe you didn't allude it, that there is sort of like an upper limit to the redshift of a hot dog, 4.6 or something. Put it in another manner. Do you think that since we need enough time for a supermassive black hole, for a QSO to build up, and to have all this material around it, do you think that it's likely that we will detect hot dogs at redshift 5 or 6?
That is a very good question that I have in mind if I have a student or something. This was could have happened in romantics, actually, but I think it's sufficiently complex that it requires you have to do a proper. I think there are public fields already in which you could kind of try to mimic the same color selection of hot dogs to try to, because JWST is much sensitive, right? So it may be that they exist, these type of sources exist even at redshift 5. I mean, we don't know because the selection bias of basically the depth of the WISE survey was just enough to stop detecting sources with luminosities of 10 to the 14 and below at redshift larger than 4.6 or 5, right? So it's very difficult because you need wide surveys and JWST is only looking at cosmos,
right,
and all that. So you have to be very lucky to find one of them. But if you find it, it would be fantastic. But we don't know. That's the question.
Okay, so there is no let's put it. There is no theoretical upper limit. Let's put it that way right now.
Not to my knowledge. No. I mean, the odds goes against you in the sense that you can only produce this gigantic amount of power during short periods of time, right?
Right.
The more high in luminosity you go, the least frequent this should be. And the higher redshift you go, the less available gas content you have in galaxies, right? Because the gas content, goes down after the cosmic noon as well, right? So the availability of gas is less.
Not enough molecules.
Not enough.
Okay.
So difficult, but worth trying, I think.
Okay. If there are no more questions, and I don't see any, I would like to thank again Tanio and everyone for joining in. And for the people who are here, we'll see you over the next few days. For the people who are away, thanks for joining in. Bye, everyone.
Thank you.
Thank you. Bye.